Hey guys, Kylo here. The techniques that are described in this video are not for the beginner pilot. Do not go out and fly in thermal conditions unless you have been trained, experienced, or have a good mentor or instructor available to help guide you through the process. It takes years of practice to become proficient at flying in thermal conditions. The techniques that I describe in this video are for the seasoned pilot or those who are at the level that they are ready to tackle thermal flying. With that disclaimer, I give you the Kylo weather video. Are you with me? Can you hear me? Hey guys, Kylo here. This is the weather video that I've been talking about for quite a while now. So, where do we start? There is so much that is going on with the air. And that's just what it is that we're going to talk about is air. What causes it to move? Let's start there, the sun. The sun is what powers everything. Free flight, soaring, it's all because of the sun. Any movement that we get to the air is from the heating and the cooling, evaporation, condensation. All these things play an integral part in the way that the air moves. The atmosphere that we live in, that is our element. It's an ocean. A lot of times people mistakenly think that it moves like water. There are some similarities to it, but it is not water, and it moves differently than water. Water is denser, it has way more pressure. Air moves, you can move it with your hand. If there was smoke in the air, and you did that, you could see it. Of course, you would see it if you did it in water too, but it's going to move completely differently. From the perspective of a paragliding pilot, a soaring pilot, a bird, we're not looking at big weather systems. We're looking at it on more of a micro scale. Not what's happening across the state or across the country, but what's happening across the street, across the yard. The difficulty in explaining it is, where do you start? What conditions do you start with? Because it's always changing, it's always fluxing. I think we should start just on the calmest day, right? No movement to the air. Over the course of a night, everything cools, settles. So what's the first thing that happens? The sun rises, and the heat from the sun starts heating the ground. The air starts to move. It starts to flux. And if you watch it on time lapse, the sun doesn't actually heat the air. It heats the ground, it heats the buildings, the trees, the concrete, the roads. Everything gets heated by the sun. Initially, the sun is at a very low angle. You're not getting a lot of direct sunlight. It's cutting through a lot of atmosphere to get to this spot. So the movement is very mild. It's very damp, but you can see it. If you ever look at a morning fog layer, you can see it slowly start to rise, and then it loses steam, comes back down, and then it gets a little warmer, and it comes up a little more, and then it settles. And you can see these are the very first thermals of the day. Dragonflies, they'll ride those thermals. I've seen them mornings and evenings when the thermals are very light. They'll go out there and soar in those early morning and late evening thermals, and you can see it plainly. But you got to know what you're looking for. The air is invisible, so these are things that you don't see. Unless there's something in the air that makes it visible, it's invisible to the naked eye. You look at the air in the morning, it's like, I don't see anything. It doesn't look like much. But there are clues and there are hints. There are things that you can see that are in the air: bugs, birds, clouds, dust, leaves. All these things are indicators of what the air is doing. And if you know how to look for it and what you're seeing, you can start to learn things. And then if you put yourself in the air, such as a paraglider pilot does, we can feel these things happening as well. Let's move on from the still early morning air, and let's just say, for example, there's a breeze blowing. You've got what they call the meteorological winds. And the meteorological winds, or the Meteo winds, are this block of air that I'm talking about moving along. And then inside of that air, you've got a lot of things happening, and I'm going to try to touch on all of them, and this is difficult. You've got this air moving just all as one, this laminar air. All right, there's no heating, there's no cooling, there's no up and down. It's just The air is moving as one. And we're only talking about kind of the lower couple of thousand feet, right? Just the air right that you're going to be flying in. We're not talking about high. We're not talking about far away. We're just talking about within 1,000 feet. That's where we're going to start, is close. If you were to fly in it, you wouldn't feel nary a bump, just smooth sailing. But then the sun starts heating the ground. And what happens is you get these little bubbles that start to come up and down, all right? And those are the thermals. So as the day progresses, the sun gets higher and higher and higher in the sky, and you get more direct heating on the ground. During the winter months, the sun is at a steeper angle. It's lower in the south. And then as summer happens, the sun becomes higher, and you get more direct sunlight on this part of the world, at least in the northern hemisphere, right? Southern weather too, but we're talking northern hemisphere. Okay, so the block of air is moving, the sun is heating the ground is heating the air, and the air starts to rise. And you can see this if you ever take a look across a long stretch of flat road or concrete or a field. Even if you can see something in the air, such as this jet, you can still see the thermals rising at several thousand feet. Air can come a couple of different ways. It can come either as low pressure, which means there's less air pushing down, or high pressure, which means there's more air pushing down. So you can take the same amount of solar radiation, heat up the ground, but if the air is pushing down really hard, it makes it hard for those thermals to come up, to break loose from the earth and lift into the sky. If it's low pressure, it makes it really easy for thermals to come up, and they just fly right up off the ground. Think thunderstorms, tornadoes. That's low pressure, right? Everything lifts so far, so high. There's also convection that takes place, but that's not what we're talking about. We're talking about the microenvironment, okay? Low to the ground, thermals are not very organized. They're like tree roots, okay? You get little fingers that are coming up from all over, right? This rock, that road, this car, that field, everything is making like a little thermal, and it's all kind of busting loose and floating up. You can see these things if you look across a field, down a road. If there's something in the background, you can see the shimmer. Those are thermals. That's what you're seeing, is the air rising, and it's distorting the light. That's why you can see it. Down low, you don't really get much out of it until things really get together. So let's talk about what that means on a no wind day. All right, the thermals heat, they just rise up. There's no wind movement. The air's not moving. It's a still day. So the thermals just come up in little bubbles straight up into the air. You might get some bigger patches, you might get some that get together, but that's not a good day. That's still kind of a turbulent light. Since we're on that subject, before we continue down the road of thermals, let's talk about what happens when air moves amongst itself, because that's something that comes up in several different parts of the atmosphere. Basically, you've got about 3 things happening, and it's wind shear. Wind shear is always the cause of turbulence. Thermals rising up through the air. There's a shear that's happening as that bubble is punching through the air. It's cutting through it, so there's a shear, right? You get turbulences at the edge of these thermals that are coming up and breaking loose. Just a quick observation about thermals. Now you can consider the heat coming off of this fire as a thermal, right? It's rising up in the air around it. Look at the edges of it. It's rolling down. You've got this up and down as the edge of the thermal hits, the smoke rolls over, kind of like a top of a mushroom, or a mushroom cloud, like from a nuclear explosion. That's, nothing more than a big thermal. This is nothing more than a little thermal. But when you talk about, regular weather-related sunshiny warm air thermals, they're the same way. They're just invisible mostly. They don't have stuff in them. But this is what they look like. The center is going up pretty much uniformly, and then the edges are rolling around, and you get turbulence. This is exaggerated because this is a fire, so there's a massive heat differential as it's coming off the top of the fire. But overall, that's what you're looking at. The edges are turbulent. That's what turbulence is little eddies of air that are rolling around. Can't see them. They're invisible most of the time. Sometimes you can, though. There's also a turbulence that comes from a hard object, mechanical turbulence they call it, or rotor is something that's commonly thrown around. That's air that's hitting an object and rolling, and you get these little rolls that come off behind an object. So you'll feel it low to the ground. Can also have wind shear because the winds are blowing different directions, winds aloft. You'll get turbulence in between that, all right? So anytime you have air moving in different directions, or at different speeds. Sometimes the air can be moving in the same direction, but maybe the winds up top are moving a lot faster than the winds down below, and so you get turbulence, you get rotor in between it. Now, how fast that air is moving determines how strong that rotary turbulence eddy stuff is. So if the thermals are pretty mild, you're going to get mild turbulence. If they're very strong, you're going to get strong turbulence. Same thing for winds aloft, wind shear. Same thing for rotor over trees. As you double the strength of the wind, you quadruple the force that that wind has on an object. You get a lot more out of stronger wind than you do out of lighter wind. So that's something to consider. So back to thermals and how they're working, okay? If there's no Meteo wind, the thermals just kind of bubble straight up, right? I've not found that those days are very good, at least in the flatlands. Now, when you talk about terrain, that's another variable. There's so many variables. I'm so sorry that this is so scattered. There's no real way to put it all together into any sort of chronological sense because a lot of different things are happening all at the same time. So we just have to talk about them in some order, and the order is random that we're discussing these things. On a no-wind day, on a slope, you'll get some development, some thermal development that has some punch to it, and they'll gather up and you'll get a good formed thermal up the side of a slope on a nil wind day, on a slope, on a hill. Flatlands, not so much. Flatlands is just little bubbly stuff that pops up. It's harder to read, it's harder to get together with other thermals. And thermals like to get together. So let's step up into our next level. We've got a little bit of wind movement here now. Say 5 to 10 miles an hour of wind blowing, the meteorological wind, the box of wind that is moving along. That's your moderate to strong area, okay? That's where most of our flying should take place. It's usually okay for newer guys at the lower end, and then at the stronger end, you know, more experience, the better. But what happens with thermals is as that shimmer that comes across the ground, it starts to get pushed together and everything sort of coalesces. And as it gets to a trigger point, this thermal breaks loose and comes up. So just for a minute, let's pretend that the droplets of water on the windshield are thermals. So there's a speed that you can go where the droplets will stay kind of bundled up, just ball up together, and the droplets will get real big. If you go slower than that, they start to drift down the windshield. Gravity takes over, right? You speed up a little and they all start to build and flow, and they form these big droplets that want to roll off the windshield. Now, if you start going fast, this is a high shear. All right, the droplets are getting sheared into tinier little droplets. They're just getting wasted, right? I was thinking about it the other day. It's a pretty good description of the way thermals drift in the wind. If there's no wind, they just pop off. That's like the drops rolling down the windscreen. And then on days that it's blown out, they just get shredded and little bitty drops streaking across the sky. But then there's the days where the droplets get big and they all boil together, and coalescence is the term. That's what it's called. And if you've got the right wind and the right thermals that works together, those are your best days. If the thermals are strong and the wind is strong, good day. Thermals are light, wind is light, pretty good day. Somewhere in the middle though is optimal, where the thermals just, when you get in it, you're in it, and you find the core and it's easy and it blasts you up into the sky. That's good days. Good days. If you ever touch one, you'll know what I'm talking about. You can learn so much just by watching a time lapse of the sky. Watch the clouds, the way they grow, the way they dissipate, what it looks like when things develop. You know, you can see the clouds suck, the moisture and the air getting sucked up through the center of these big ones. I found nothing better to learn the way the sky operates than to video it for an hour and then watch it over 20 seconds. Let's talk about buoyancy to shear. Throw in yet another variable. If it's a high buoyancy, low shear, right? We got strong thermals and we've got light winds. And that means that the thermals hold together. They don't get chopped up by strong winds. If it's a low buoyancy to shear, then that means the shear is high. And so you get the little shimmers coming up and the wind just rips them off, gone. That little bubble forms a tiny thermal and it gets mixed into the wind. Everything just gets mixed up. It's like a blender, right? You hit puree on the blender and everything just turns into a mess. And that's what happens on a strong wind day or a light thermal day. Everything just gets chopped to pieces and it's not really readable. But the good day, the 5 to 10 with good strong thermals, those are the good days. That's when all the thermals get bubbled together and they form these columns of lift, these thermals. They're being fed from these tiny little feeder thermals at the bottom, forming a column, and then they go into the sky and ultimately, hopefully, form a cloud top, a cumulus cloud at the top. And if you see the cloud and you know where the source is and you know how to read the wind, you can figure exactly where that lift is. And if you get in that lift, you can stay in it and you won't really lose it because of the shear, all right? High buoyancy to shear. This is a good day. This was about 10 a.m. on a day that produced several 100-mile-plus paragliding flights during a competition in South Texas. Cloud streets stretched into the distance, good cohesion between the thermals, just banging away. This is what you're looking for. If you see this, go for it. That's a good day. That's what we're looking for. Good thermals, good winds, like everything is in a nice window. When you hear about a good day, when pilots talk about it's a good day, that's what they're talking about. They're talking about some lighter winds on the bottom, maybe stronger winds aloft, but the thermals are held together, and that means that you can use them to fly high and far. That's what the birds do. Birds are better at it than us. They can use light, little, tiny thermals down low to the ground. Not so much for the for paragliders, hang gliders. We need big thermals, you know, at least big enough that we can turn in them and stay up, not just go in and out of them, in and out of them. You want to get in the lift and stay in the lift to go up. And we're talking about this from a paraglider, hang glider perspective here. So we've got some wind, we've got some lower pressure, we've got some sun, we've got some heat sources on the ground. Everything is kind of finding its groove, and that's what we call cycling. The air will cycle. You'll get a thermal that'll break loose on the ground. Now, if you were just sitting still on the ground and this air is moving by you, and you get a thermal that breaks off upwind of you, the wind is going to lull. Your windsock is going to point down, possibly even point back at that thermal, you know, into the wind that's been coming at you. As that thermal breaks loose, air is going to come in from underneath. And what you'll see as somebody on the ground observing is the wind that's blowing will lull, and then as the thermal breaks loose, everything will come back out. If the thermal breaks off downwind of you, what you'll see is your windsock will point out. You'll get a gust and that wind will increase as that thermal goes up and the air is sucked in from underneath. Same thing can happen from one side to another. You'll get directional shifts in your windsock. And that's why the windsock moves around during thermal conditions. You'll see it spinning and swirling and it just looks random, but it's not. It's always going to be pointed at whichever way the thermals are breaking off. So if you're in the air and you can read that, you know which way to go, okay? Let's talk about winds aloft now. All right, there's always some degree, it's about that much. You got surface winds and you got winds aloft. Even if they're the same direction, you'll get about a 30-degree angle on the winds aloft, and they'll usually be stronger, and everything kind of turns as it goes up. And that's due to the Coriolis effect. The world spinning causes friction on the wind, and it changes the direction lower to the surface than it does aloft. So you'll always see an angular change. You know, if it's blowing straight out of the south, you can just about bet that the winds aloft are going to be ticked out of the west in the northern hemisphere. That's something to look for as well. Winds aloft and thermal strength are the two biggest things that you want to check for as a new pilot to make sure that it is not over your head. If the thermals are real strong or the winds aloft are real strong, that could be a no-go, right? That could be a bad day. If the thermals are too strong, they could develop into thunderstorms. You know, you get convection. Convection is when the moisture in the air condenses and releases heat again and causes cloud suck. And the cloud suck, that's what we call it, but it's a convective activity that causes its own amount of suction to form. That's why you can have thunderstorms at night when there is no sunshine, and it's why they can happen over the ocean. It's convection. They develop their own energy. It gets to a point where it's like a runaway train, right? A snowball effect, if you will. You get a little cloud puff, swells up, cumulus cloud, and it dissipates. And that's typically what you see through the course of a day. Now again, we could go on. There's textbooks this thick written about the weather. And it's still stuff we don't know about it. The data, the computer models, like they're wrong a lot of times. It's not a hard science, but there are some things that we understand, and there are some things that indicate what the air could be like for us as pilots and what we need to be looking for. And then there's the pilot. Not every good day is good for just any pilot. A seasoned pilot is somebody who's experienced several different forms of the atmosphere. Still days, windy days, thermally days. Once you can handle all these things and you start to kind of form a mental image of what's happening with the air, then you can progress as a pilot. Something else is going on as well, okay? So let's talk about thermal some more. You've got this column that is lifted into the air, the wind's blowing, they're going to be leaned over to some level. Most people have it in their mind that they're leaned like this. It's probably more like this. A good thermal on a good day is probably leaned over way more than what you think it is. So this is the column of air on a strong day. On a mild day, maybe it is like this, right? On a no wind day, maybe they are going straight up. Sometimes they're shaped like bananas. You can have a wind going this direction, that direction, and you can have a thermal column that's bent. You know, it's going this way and then it takes a dog leg because the winds shift at a certain altitude. These are things that you have to learn as a pilot, and it's not something that you can see easily. Having a Vario and with maybe a GPS tracker that gives you wind direction, that's good. That's something that you can use to determine what's happening with the air, and it'll make you a better thermal pilot overall. So as you've got this thermal leaned into the wind, okay? The wind is blowing it. That's what's causing it to lean over, obviously. This sea of air that's coming into it, as the air hits the front of the thermal, it actually goes up a bit and around it. The air that the thermal is made out of is denser than the air that it is climbing up through. The wind that's blowing, it hits this thermal. It's almost like it's hitting the side of a mountain. Obviously it's not. It's way less dense than a mountain, but the air will hit it and some of it will go up, some of it will go around. On the back side of the thermal, you get a couple of things. It's worse to fall out the back than it is the front. On the back side, you've got this air that's coming around the thermal and it's coming down. You've got the sink on the outside of the thermal, the lift inside of the thermal. But on the upwind side of the thermal, you've got air hitting this thing and it's pushing up. Even though there's some coming down in the front, you'd rather punch out of the front side of the thermal than the back side. If you fall out of the back, you lose a lot more than if you punch out of the front. That's something to consider as well. When you're thermaling technique, it's never just a circle. So let's talk about the pilot. Let's talk about what you should do as a pilot to properly use these thermals to climb and to go far with. You know, you don't have to have a motor. Kill your motor and use the thermals to go up and about. It's great. Sometimes they all line up. If you back out into the bigger picture, the thermals all form in a line. Get a street of thermals that are all, you've got lift going up, and ultimately up top what you'll see is a cloud street. Cloud streets are lines of lift that have come together. You got the little stuff at the bottom feeding the bigger stuff in the middle, and then ultimately at the top, everything kind of wants to get in line with each other. So you'll have lines of lift. In between, you'll have lines of sink. Then you'll have another line of lift. And these are called cloud streets. If you ever get streeting, that's good. That means you can get in that and you can just really go far with the weather. And that's how pilots are able to go hundreds of miles on paragliders and hang gliders without even having a motor on board. Just using a cloud street, a good lift line, that's how you do it. And that's what we're looking for. That's a good day. That is a good day. So how do you work your way up to that? What's good thermaling technique? Let's talk about it for just a minute. So as you enter the thermal, you will feel turbulence. You will feel bumpity, bumpity, bump. Sometimes they're wild because the thermals are strong, and sometimes they're not because the thermals are weak. Now, weak thermals are harder to climb in because they're weak. Strong thermals are more dangerous because the edges tend to have more turbulence. Maybe you take collapses. Thermal flying is not for the unseasoned pilot. This is for the pilot that knows how to handle his glider, that has taken an SIV course, that can handle collapses without getting freaked out about it. They know how to recover. You've got a reserve parachute. You've got all your safety instruments in place. You're over good terrain. Again, variables. Lots and lots of variables are going to come into play when we talk about doing the stuff that we're doing here. But strictly talking about piloting, and what you should do as you enter a thermal is you should immediately try to figure out where you're at in this thermal. If you know where the wind is, and if you're going with the wind, you can expect if you hit a thermal, you hit somewhere on the front side. So a good rule of thumb is to count to 3 or 4. 1 1,000, 2 1,000, 3 1,000. If you're able to count to 3 and you're still in the thermal, it's probably a good sized thermal you can turn in it. So you don't just pull a brake and start a turn and fly a perfect circle. You'll fall out of the backside every time if you do that. You have to change your turn as you traverse this thermal. So it's a good day, the thermal is leaned over. As you go into the thermal, 1 1,000, 2 1,000, 3 1,000, the first turn needs to be, it could be a circle. You could do a circle unless you know you're in the core and you know where it's at. You felt one side of the wing lift or the other. You know, if you feel your right side go up, maybe you've hit it on the left side, and so you know you need to turn to the right. If you feel the left side pull up, maybe you've hit it from the right and you need to turn left. So once you establish yourself in the thermal, you figured out where the back is, you figured out where the front is, you've oriented yourself inside of this column. Now you want to fine tune your piloting skills. You want to affect your turn as you go through the thermal. As you go downwind, you want to increase your turn so that you really whip it around hard so you don't fall out of the back of the thermal. You want to turn really hard, and then as you come into the front side of the thermal, you want to level out, and you'll usually go up, 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 up. You'll hear the beeps. You'll be climbing like crazy. When you're just about to turn out of the front of it, you'll start your turn again, and then of course, as you come around and go downwind, stronger turn, steeper bank. You come down, you come up with the outside brake, wheel it around, back in, up you go, then turn. Go down, turn hard, come up, down, turn hard, come up. And it's a timing. You got to find your rhythm. If you watch a bird, you'll see how a bird does it. They'll go into the wind, into the wind, into the wind, and they'll turn and they'll whip it around, and they'll into the wind, into the wind, into the wind. They'll turn and whip it around, and then and you just keep going up. You'll maximize your climbing if you'll do that thing. You never really stop turning though. You always stay in a turn, but it's never just a solid circle. Inevitably, if I've ever just turned a solid circle, I'll fall out of the back of the thermal at some point, or the front, or the side. You've got to kind of feel it. You've got to measure it. There's almost no words that I can explain it that's going to make you do it. You just got to go out there and do it. But these are just some tips that I've learned over the years of doing this that have helped me make better climbs out of the thermals that I do get into. And I hope that you'll do the same. What's happening on a too good of a day? Maybe the winds are really strong and you lose that buoyancy to shear. Again, it could just be a washing machine. Think thunderstorms and tornadoes. Those days are too big. That's overdevelopment. You see that the clouds are climbing like really, really high, super tall, big clouds everywhere. Maybe there's rain falling in a couple places. Sometimes those are good days to fly, as long as you don't put yourself too close to a cloud that's getting too big too fast. You're usually okay. But again, you've got to keep an eye on the weather. You can never let your guard down on a day that could overdevelop. Again, guys, we just scratched the surface on this. This is not an end-all, be-all, how to weather video, but we're getting there. We're getting there. And the only way to really do it is to go out and practice and to learn it. So I hope you liked the video. If you did, consider giving it a thumbs up. If you did not, There's also a thumbs down button. In the meantime, I'm going to keep making content, and I hope you'll keep watching it. For those of you that are liked and subscribed and all that stuff, much love to you guys. For the Patreons, thanks a lot. You guys really help make this stuff happen. I hope I can share as much as I know. There's so much going on with the weather that it's almost impossible to put it into one video. Again, textbooks this thick on the topic. We're just scratching the surface. I hope you'll subscribe for more, and we'll keep talking about it, and we'll keep learning from it. Around and around we'll go. With that said, much love, everybody. Kyle out.